So, since I'm almost the last speaker, I would like to take this opportunity to congratulate the organizers, which has been a wonderful, wonderful conference, really covering giving a bird's eye view of this very broad field of string theory. It was great to hear all these very important and concrete developments on so many fronts. So it tells you that our subject is in good health. And it's also good that they decided to encourage younger participants, younger researchers to present their work, and we heard many exciting talks. And I'm also happy to be included among the young ones. So, okay, so this is some work done in collaboration with Upamanyu, who you can see here taking a selfie. And it's also the 60th anniversary of ICTP 2024. So I just want to, that's why that logo is there. So I want to tell you a bit about quantum entanglement and string theory. So entanglement entropy is of fundamental importance in quantum mechanics and quantum field theory that we know. But I would say even more so in quantum gravity, because finiteness of entanglement entropy is really at the heart of black hole information paradox. So my goal is to whether we can define a notion of entanglement entropy, given the fact that string theory is a finite UV finite theory. What are the motivations? What are the difficulties? And I'll propose a method. So if you take a black hole, you would be tempted to split the Hilbert space into the inside of the black hole and outside of the black hole. And if you trace over naively all the interior, you'll get a density matrix rho naught whose von Neumann entropy diverges. This is a well-known calculation. It's proportional to the area and it diverges. And this seems to suggest that we have infinite number of qubits stored inside a black hole. And this is really at the heart of the information paradox. And to really go beyond this in string theory, we would need some generalization of von Neumann entropy, because the usual notions from local quantum field theory, like algebra of local observables, is not available in string theory. So let me just quickly remind you of the classic quantum entanglement in quantum mechanics. The classic example is the Bell pair with spooky long-distance EPR correlations. So you have two photons, one goes to the left to Andromeda galaxy, and one stays at CERN. And if you are performing an experiment at CERN, we can basically trace over what is happening outside. And they are in a maximally entangled pure state, up, down, minus, down, up, in the bipartite Hilbert space, which is very different from an unentangled pure state. And this is, as you know, is kind of formalized. You have a state which is normalized to 1, then you define a density matrix normalized to 1, then you define the reduced density matrix rho right, which is in this region, by tracing over the left Hilbert space. And this is sufficient to study all correlators in this room or in this laboratory. And this is the fine-grained von Neumann entropy. And for example, for the maximally entangled Bell pair, the von Neumann entropy is log 2, and 2 is the number of dimensions. So that gives an indication of the dimension of the Hilbert space that you're tracing over. Sorry. And if you try to do it in quantum field theory, now we are in this room, and this wall, whose coordinates I denote by y, which are the transverse coordinates of the y, and you have x positive is in this room, and x negative is outside of this room. So you're dividing space between x left and x right. And again, you would be tempted to divide the Hilbert space into left and right, and define for the Minkowski vacuum the density matrix and the reduced density matrix. And if you compute the entanglement entropy, it has an ultraviolet divergence. And this is an area law, so it looks like it has something to do with black holes, and it has a UV divergence. And this is related to Rindler spacetime, because if you take a Rindler observer, accelerated observer with acceleration going that way, then a Rindler observer will come at the speed of light and get stopped somewhere, and she will go back. So she will never be able to cross the wall. And so therefore, from the point of view of the Rindler observer, the reduced density matrix is the natural quantity to consider. And it can be written then in this picture, simply as the Hamiltonian of this accelerated observer. It really has, this is the exponential of minus 2 pi kr, and 2 pi is the Rindler temperature, 1 over the 2 pi. So, and the Rindler metric, as you know, is basically the Euclidean continuation of the spherical coordinates on a plane. And it has a temperature which diverges, and there is a simple intuitive way to understand it, what the divergence is from. As you know, most of the really important physics comes from this point on the Penrose diagram, which is the bifurcate horizon. And if you have a fluctuation, quantum fluctuation going around for the Minkowski observer, for the Rindler observer, it looks like it lives forever. And there is a bell pair, one which is on this side and one which is on that side. And as you can see, as you come closer and closer to the horizon, you go into the ultraviolet. It's color-coded, as you can see. So the violet is violet. And that's a very quick way to understand the ultraviolet divergence. Now, this is not, there is a different formulation, algebraic quantum field theory, is because, so I just want to refer to it very quickly. It's not quite correct to assume that the Hilbert spaces are factorized. And the main reason is that in local quantum field theory, there are strong correlations between, I mean, if you think of it as a spin system, then the kinetic term is basically forcing both the spins to be aligned. And so if you put a wall, artificial wall, that correlation is broken. And that's really is why we cannot really think of the Hilbert space as being factorized. However, you can always think of in a local quantum field theory, the observables, local observables being factorized. So the algebra of observables is factorized. And for that reason, it is useful to use this somewhat abstract formalism that we don't normally use of algebraic quantum field theory. And you can define in that language, if you're not familiar with it, don't worry about it. Minkowski vacuum is a cyclic separating state. There is a von Neumann algebra, which is like an algebra with some properties of addition that are well defined, some kind of limiting procedure well defined. And then in this picture, the fact that you have a UV divergence is not a property of the state, but it is the property of the algebra. What kind of algebra you're talking about. And there is a type 3 algebra, and the quantum field theory seems to be like a type 3 algebra. Roughly speaking, it means that it does not admit an irreducible representation, as opposed to the bell pair example that we considered, where it is a type 1 algebra, where clearly the algebra of observables in this room furnish a irreducible representation on the right Hilbert space. And that doesn't happen in the type 3 case, and that's the origin of this. And this algebraic quantum field theory, the advantage is that now the boost operator that I told you about follows as the modular Hamiltonian in this Tomita-Takesaki theory. And you can define quantities like the relative entropy and prove interesting theorems like strong subadditivity and so on, and in a completely general way without assuming weak coupling in a strongly coupled quantum field theory. And one of the two things I want to mention to you, because that's the motivation, there are a couple of examples in the quantum gravity context where it has become clear that it is important to have a notion of entropy, quantum entanglement. One is the generalized second law of thermodynamics as envisioned by Bekenstein. And there is a beautiful proof by Wall, which basically follows from the fact that the relative entropy that I defined on the previous slide is monotonically increasing under inclusion. And relative entropy, because it is defined in algebraic quantum field theory, is completely free of UV divergences, because in algebraic quantum field theory, there is no cutoff. You don't have to talk about divergent quantities. However, if you look into the proof of Wall, it's necessary to use the null-Roy-Choudhury equation to relate the change in entropy energy term in this to the area term. And that quantity, even though the two terms in the in the relative entropy by themselves are UV divergent, the total quantity is not divergent. But to prove this generalized second law, you really need to define. It's a good idea to have this definition. Another thing is the strong subadditive paradox, which has been talked about a lot. Once again, they are talking about entanglement between the modes near the black hole, inside the black hole, and it would be good to have a well-defined notion of entanglement entropy. So these are the motivations. Now, how do we proceed? There is a very nice, very general path integral formula for computing the entanglement entropy. And that goes as follows. And actually, it's a remarkably general formula which applies again to any quantum field theory. If you look at the wave functional of the Minkowski vacuum in the field basis, then you know that if you evolve from minus infinity to today, the slice, then you know that in the Euclidean time, then basically only the ground state will contribute. And therefore, you will automatically, by doing this path integral on the past, you will get the you will get the wave functional of Minkowski vacuum in the field basis. If you evolve it from the future, then you will get the wave functional of the bra in the field basis. So since you are interested in doing bra times ket to get the density matrix, this is the density matrix representation. Matrix elements of the density matrix are given like that because you're tracing over phi left. So whatever are the field degrees of freedom outside of this wall, you're tracing over them. And that's why you identify this phi left prime with phi left and you integrate over it. And that is therefore represented by a very nice path integral in a cut plane. And where the boost operator that I talked about becomes the rotation operator after this Euclidean continuation. And Minkowski vacuum, you can do some Bogoliubov transformation, and is basically, again, a collection of lots of Bell pairs. So it's really connected to the very simple example that we started with. And then it's easy to define Renyi entropy. Given the density matrix, you can take its powers and define the trace, and then you can take some kind of a, so you will get basically a stack of planes, and the opening angle therefore is not 2 pi, but 2 pi n. You will come back to yourself after 2 pi n, and so you have a kind of a surplus opening angle bigger than 2 pi, and the entanglement entropy is obtained by doing an analytic continuation in n and taking a derivative. And this is quite a general formula, and it has been used quite a lot in quantum field theory with many interesting results, and many people here are experts in this. And we have learned a lot from entanglement entropy in quantum field theory. Now, this unfortunately doesn't work in string theory because string theory does not allow you to just do whatever you want. In particular, doing this kind of a stacked of plane is almost impossible in string theory because it does not solve, string theory would not make sense. However, string theory makes sense on orbifolds as exact conformal field theory. So instead of the idea of generalizing the replica method to string theory is that instead of using the n-fold cover of the Euclidean Rindler plane with a surplus opening angle, why not consider a cone with a deficit opening angle? And the cone can be obtained simply by taking an orbifold of the plane. It's a C mod Zn orbifold, and the capital N would be 1 over, if you could analytically continue, would be like 1 upon n, in where the n was, small n was the replica n. And so you can define, I put a hat to indicate that it's a string field theory partition function. So it's really a space-time partition function on a cone. And it would be, by the same logic that I gave you, it will be minus 2 pi times the Rindler-Hamiltonian. Rindler-Hamiltonian was just the Lorentz boost. And now the temperature is not 2 pi, but 2 pi divided by n. So you're computing this quantity. And now the entropy is defined by the usual formula with beta is equal to 2 pi divided by n. And this cone has a conical singularity at the tip. The Ricci scalar is divergent. It has a delta function singularity. But as you know, in string theory, even though general relativity, canonical gravity is divergent, string theory is perfectly well defined. And it has a deficit angle, 2 pi 1 minus 1 upon n. So we can actually, as is known, for higher loops, one can relate the logarithm of the space-time partition function to the worldsheet partition function by this formula. And I will not go into it, but it's roughly like you're summing over one-loop diagrams, which are like the bubble diagrams, and you're doing exponentiation. So the space-time partition function will give you e to the power of the bubble diagrams, and you take the logarithm that gives you the worldsheet partition function. And so this gives you at least a formal definition. If you could define these partition functions of, this should be, if you could define the partition function zq of n, then we should be able to compute the entanglement entropy. So now let's go ahead and construct these orbifolds. And the worldsheet partition function is relatively easy to compute. So you take type 2 string theory and light cone gauge in R6 cross C. and the C is my Rindler plane. I consider the Green-Schwarz superstring. So those of you who are post-holography and may not remember your worldsheet calculations, let me just quickly remind you. So on the string theory, as you know, there are 8 bosons and 8 fermions going left and 8 bosons and 8 fermions going right. So you basically do the group theory, spin 8 you divide as spin 6 times spin 2, and you embed this Zn inside the spin 2. So you just need a decomposition of the vector spinner and the conjugate spinner, and it is given by this. And the main point I wanted to notice is that, as you would expect, 6 bosons are neutral. They are not affected by rotation carried out in a plane. 2 of them are charged, and all the 4 fermions are charged, but the charge is half because spinners have half charge. So that's the only thing that you need to know. You have so many free bosons and free fermions. 1 complex boson is charged, and 4 complex fermions are charged with half the charge on both sides. And therefore, the generator for this Zn symmetry is just the 4 pi I divided by n times j. 4 pi because you don't come back to yourself because of spinners. So you put j, which is basically the Euclidean Rindler boost. And you take n to be odd. And again, the partition function then can be very easily written down. If you take the twist along this direction to be k and the twist along this direction to be L, then because I told you, I can just quickly explain this formula. You have theta to the power 4 k tau plus L upon n, and theta, just a single theta with 2 k tau plus 2L divided by n. And this can be very easily understood by the fact that you have 4 complex fermions, which sit usually, fermions give you a product of 1 minus q to the n product formula. So this is theta to the power 4 comes from 4 complex fermions, and this theta comes from a single complex boson. And it is proportional to the horizon area as you would want. So now UV and IR divergences. So the original motivation, as I said, is that we know that very well that if you put the theory on a lattice, there is no ultraviolet divergence. And string theory, in a way, is providing a UV completion of the theory at the perturbative level. You don't need to do large n, finite n corrections. So you expect that already at the perturbative level, there should be UV finiteness. And that's the good news. But then the spectrum is replete with tachyons because you are breaking supersymmetry, and they're all localized at the tip of the cone. Because exponential, roughly speaking, you write tau as tau 1 plus I tau 2. Tau 2 can be interpreted as the Schwinger parameter. And exponential of minus 2 pi m squared tau 2 are the kind of terms that you'll get when you expand q to the power something. And it diverges when the mass is negative. And there are lots of mass square is negative. And there are many, many tachyons whose mass square is negative. So that looks like a problem. It looks like string theory doesn't buy you anything. You have just exchanged a UV divergence for an IR divergence. But as you know, UV divergence and IR divergence both are divergences, but they are completely on a different footing. UV divergence is a matter of regularization, where IR divergences contain physics. For example, yeah. So now, one observation that was made by Witten in 2018 was that tachyons need not be a cause for despair. And his argument was that in quantum mechanics, if you have trace rho to be 1 in an infinite dimensional Hilbert space, then trace rho to the power n must converge, small n, because you are raising small numbers smaller than 1 to a large power. So they will converge even better. But if you take the square roots of the numbers, for example, 1 upon n, there is no argument that they have to converge, and it may diverge. And so maybe the tachyons are an indication from string theory that this is what is happening. And to do that, we actually need to do analytic continuation in the physical region, which would be n positive integers. So that means capital N less than 1. So the physical region would be this 0 less than capital N less than or equal to 1. But you need to find some analytic continuation given the data for n greater than 1 for n odd. And this was actually achieved for the simpler problem of open strings, and I will come to that later at the end of the talk. And under certain conditions, the Carlson theorem, there is a theorem which basically guarantees the uniqueness of this kind of an analytic continuation. And it should not look too surprising to you. You are sort of used to this, that if you have an analytic function, Just knowing its derivatives of the origin in the domain of analyticity, you can construct the function completely, and its uniqueness is guaranteed by Cauchy's theorem. This is a little bit like this. Okay, so I should rush. So now we want to do this kind of analytic continuation on the Rindler horizon, and this is our partition function that we have written down. And it's quite hard to do this in closed string theory, but what we can successfully do is that you can look at the exponentially growing terms in this partition function, and it's easy to see that it looks like a complicated sum, but fortunately it sums, you can actually sum it exactly, and you get this answer, which you can see diverges when n is less than 1, but converges when diverges when n is greater than 1, but converges when n is less than 1. So remarkably, all these tachyonic diverging terms disappear when you go to the analytically continued answer. I want to emphasize that this fact is not accidental. It's really something that depends on some just so properties of string theory, that there are exactly n-1 twisted sectors, each containing tachyons. In the k twisted sector, there is precisely one leading tachyon whose mass squared is linear in k, and there are many subleading tachyons, but they all come with unit multiplicity. So all these three facts were important for us to be able to do this calculation, so I believe that it is not accidental. There is I will maybe come back to this later in view of the time. One can actually compute the classical entanglement entropy, but we generalized this to, we said that, okay, maybe this analytic continuation was a very special property of 10-dimensional superstrings. What about some Calabi-Yau manifold when there is less supersymmetry? And in particular, if you take Calabi-Yau orbifolds, there is a possibility of doubly twisted sectors having new tachyons, and there is no guarantee that the same method will work. So we analyzed this, and until we had finished the calculation, it could have gone either way. So just to give you an example, if you consider a T4 mod Z3, the simplest orbifold, it has new tachyons in the doubly twisted sector. It's not a priori obvious, but you can actually do the analytic continuation, and the same story works. Then we did heterotic string theory, where there are new subtleties because it's a chiral theory with potential for gravitational anomalies. Modular invariance is more tricky. Gauge symmetry must be broken. And once again, we were able to construct the model and also classify all the Zn orbifolds such that the tachyons can be analytically continued. Finally, we did entanglement on black hole horizons. So this ADS 3 cross S3 cross T4 example, there is an exact conformal field theory. And this work goes back to Kupiainen and Uguri and Maldacena and Polyakov and Wigman. Using these techniques, you can actually do this exact world sheet theory partition function for a BTZ black hole at finite temperature. But what we're really interested in is Zn orbifolds of the horizon of the BTZ black hole. And I have to say, I was surprised that we could actually do this exactly. You can write down the explicit partition function even for the Zn orbifolds, and you obtain a function which is generalization with all these four quantities, the n of the Zn orbifold, mass of the black hole, spin of the black hole, and k, which is like the ADS radius. And once again, you find that all the tachyonic divergences are nicely analytically continued. So what about, can we do an exact analytic continuation? This is some work in progress with Don Zagier, and I just want to quickly tell you how it is done. So typically, we need to perform finite sums of the form, some function of k and l, which depends on things like e to the 2 pi I L upon n. And basically, this function, for this sum to be defined, n has to be an integer. So you need to obtain a form of this sum such that n can become a complex number. And one simple lemma that, well, simple if you have a good number theorist as your collaborator, is this lemma. And there are actually 3 one-line proofs, and you can stare at it and try to prove it yourself. But it's true. But the main point I want to emphasize is that on the left-hand side, n has to be an integer because you're looking at the nth roots of unity to sum over. But on the right-hand side, n can be a complex number. So that's the kind of formula we need. And using this, we were able to actually do the open string calculation exactly and in perfect agreement with what Witten obtained. And we can basically do it in 2 pages, which takes, Witten used some generalization of Sommerfeld-Watson method by some contour deformations. And we can reproduce that result very simply using this lemma. And again, I want to tell you that the partition function looks like this. It's a sum over some numbers, but now n doesn't have to be an integer. And I'm done. This is my last. And once again, as I had told you, the disappearing tachyons that we observed in closed string theory, here you can see it very explicitly for the full function. If you go from the open channel, because you're evaluating a one-loop partition function of open string, if you pull out the open string and look at it as a closed string channel, so that it's a closed string propagating, then in the IR limit, there are tachyons propagating when n is capital N is greater than 1. But in this analytically continued formula, they disappear. So I think my summary is that the orbifold methods offers a stringy generalization of the replica method. We have presented substantial evidence that this method could give rise to computable entropy that is finite both in UV and IR. The IR divergences have a very specific structure dictated by string theory. So I think given our experience with string theory, I think it's wise to pay attention to what the string is trying to tell you. And one obtains a natural order by order expansion, which could be a generalization of the von Neumann entropy. I didn't have time to go to about the tree level, but a tree level term also comes out very naturally. And so perhaps this notion of entanglement entropy in a complete theory of gravity like string theory is perhaps a more fundamental notion than the black hole entropy. And black hole entropy is just a particular example of that, where the horizon is not, inside the horizon is not accessible to us. And there are three open problems. One is, of course, how to find the analytic continuation, which is something work in progress. It's not easy because it's a difficult problem, but I'm, let's say, cautiously optimistic. In string field theory, and this is a homework problem for the string field theory colleagues, that can string field theory be used to compute the boundary terms which are necessary for computing this tree level contribution, especially because the C mod Zn is a very well-defined and simple conformal field theory, explicit exact conformal field theory. And the conformal field theory correlation functions is the data that is required to define the string field theory. So I think it's a good laboratory. It's the closest analog to, let's say, sense conjecture about the brain-anti-brain annihilation, where you had something to shoot for from some other reasoning. And here we know that the action has to be 2 pi divided by n. So there is something, homework problem. And can we map the bulk computation in BTZ background to a quantity in the boundary CFT? I mean, there are very interesting developments like, I don't know, Matthias and Lawrence is here. You can actually define bulk and the boundary at the same point, and maybe we can try to define the analogous quantity in the boundary theory. So I will stop here.
Okay, I see a whole bunch of questions. Let's start here.
So you have a physical picture of a cone and a bunch of tachyons that are localized at the tip of the cone. Is it possible that the back reaction of the tachyons modifies the original geometry?
Yeah, so if the way we have approached this currently is that we are using this as a data, like in the replica method, for an analytic continuation. As I showed in the open string case, you can actually do it completely explicitly. So there you don't worry about trying to find the physical interpretation of the Euclidean tachyons. You just use it as a data, and then you discover that when n is less than 1, those tachyons disappear. Alternative approach which I also have thought about in the past is whether you try to get the tachyons to condense. And if the tachyons condense, then the question of back reaction becomes important. But here you are really sitting at the top of the hill, and you're not yet rolling down the hill.
Yes.
Hi, I have a very naive question. Like, I'm here. Yeah. Can you comment about RT formula or subregion duality construction from your formalism? Or?
No, so I think that's a very interesting question. I mean, I didn't talk about the Ryu-Takayanagi formula because it's really all happening in the boundary. I had a couple of slides on holography and this question, but since the chair didn't...
Just a clarification. I wasn't quite clear what you were saying about the the tree-level piece, because the piece you're computing is the one-loop piece. So that has an area law divergence and in quantum field theory, and that's regulated in your calculation. But to actually get the full von Neumann entropy, you do need to know what the tree-level piece is. And
yeah, so in this,
what is the prospects of that?
No. So at the level of the calculation, actually, the tree-level answer you can calculate. The difference is that at one loop and above, the logarithm of the space-time partition function is the worldsheet partition function. This is not true at tree level, even though this is what is we naively believed. It's only true for the bulk action. And the tree level worldsheet calculation is not, we don't know yet methods of computing the worldsheet, the boundary terms like the Gibbons-Hawking term in string theory. But in my the paper in which we did compute the tree level you can give arguments that because it's an exact conformal field theory, the dilaton equations of motion are exactly satisfied to all orders in alpha prime, and therefore the bulk tree level action is 0, consistent with the fact that the sphere partition function is 0. But there is a boundary term which is basically the Gibbons-Hawking term, and which you can argue to be exact. So that gives you the answer 2 pi divided by n area. And from that, if you do analytic continuation in n, you recover area upon 4g. But it does not give you a state interpretation. It's a calculation in some effective theory.
Final short question.
Thanks for the nice talk. I'll keep it short. Could you say how you generalize what you did here for a setup with less symmetry, like multiple disjoint regions? Is that within reach?
Meaning in the same space-time, multiple disjoint regions?
Yeah, instead of half space, you can consider a strip or multiple strips. Or...
Yeah, it's an interesting question. I mean, I don't know if one can have an orbifold. Yeah, you could consider having 2 orbifold singularities, but that could be one way to do. I don't know.
Also, a super quick question. To what extent, since strings are extended objects, to what extent does this quantity deserve the name entanglement entropy?
Yeah, so as I said, we don't have a really well-defined notion, a framework like the von Neumann algebras to define entanglement entropy in string theory. So I believe that we are defining some quantity, and it's related to entanglement entropy in field theory in some limit. It's a very natural generalization. And I hope that it's a kind of an impetus to try to define what we mean by entanglement in string theory. But I think there is no, in my mind, there is no question that string theory must yield a finite answer if it is UV finite, because these divergences, so I think string theory should turn out to be not a type 2 algebra, but type 1 algebra. But how that happens is what we are trying to understand.
All right, let's thanks to Atish once again.